how can we understand how the universe was put together? How can we understand where we came from and where we're going? And one of the ways of doing that, along with many of the other ways you've heard in this conference, is to build a giant telescope.
Next up is a session that I'm personally absolutely dying to watch, is Mark McCaughrean, who's an astrophysicist and an interdisciplinary scientist looking after the James Webb Space Telescope. I'm sure all of us have heard those headlines, brilliant images coming out of 13 billion years ago to the origin of the cosmos, origin of the universe, all the way back to the Big Bang. This is an absolute mastery of science, craftsmanship. How do you build a telescope like that? How do you begin to unravel the mysteries of the universe? What we are talking about, as I said, is only 0.1% of the universe, but these are the men and women of science that are making even that little thing intelligible. This is going to be an absolute joyride into, as I said, the beginnings of the universe. Ladies and gentlemen, please welcome on stage Mark McCaughrean.
Thank you very much for the introduction, and thank you for inviting me here back to India. It's always a pleasure to come. I'm going to do something a bit different to what you've had for the rest of the conference. I'm just going to tell you a story on my own, but with the backing of 20,000 human beings who made this amazing machine, and that's trillions of trillions of trillions of molecules, some of which were made in the centers of stars, which came together billions of years later and became conscious and decided to dream and say, how can we understand how the universe was put together? How can we understand where we came from and where we're going? And one of the ways of doing that, along with many of the other ways you've heard in this conference, is to build a giant telescope and to look out into space and look across the vastness of space and time, looking back in time. The further away we look, the longer it has taken light to come to us, the further back in time we're looking. And this machine, the James Webb Space Telescope, was built over decades by scientists and engineers from NASA, the European Space Agency, and the Canadian Space Agency. So I'm lucky enough to have been involved for a very long time, and I'm lucky enough to be the person to tell you about it this morning. But it's a huge team effort, driven by curiosity, ingenuity, consciousness, and I don't think any AI was involved at all at this point. So let's start at one moment in time, and that moment in time was Christmas Day 2021, when the James Webb Space Telescope was launched from the European Space Agency's launch base in French Guiana in South America on an Ariane 5 rocket. And this enormous, powerful machine lofted this satellite into space. I will tell you why we decided to build it the way we build it, what it looks like, how it was designed, put together, and then, of course, what we've been doing with it after launch. But the story goes back even further. The story, in a way, goes back to the launch of the Hubble Space Telescope, which was in 1990, April 1990. I was involved in that project at that time as a much younger person, and people had worked for decades to build the Hubble Space Telescope. And there were many scientific aims in mind, many breakthroughs which were promised by this machine, and many were delivered, indeed. But even then, we knew that this machine would not answer certain questions. Certain questions would be outside the scope of the Hubble Space Telescope. So even before it was launched in 1990, people came together and said, what would the next generation space telescope look like? How would we build an even bigger and even more powerful machine? So in the late 1980s, when this project started, people gathered together and wrote an outline of what that machine should be. But the story goes back even further than that. Because throughout human life, the lifetime of human beings on this planet, maybe hundreds of thousands of years, we've looked up at the night sky. It's not so easy these days. I mean, you don't see too much of the night sky living in the big cities, but prior to that, we could look up at the night sky and see a sprinkling of stars, of points of light across the sky. This is a picture taken from New Zealand where you can actually see that what we now know is our own galaxy, the Milky Way. We live near the edge of this giant galaxy of maybe 200 billion stars. Our sun is a very ordinary one of those stars, but we look towards the middle of it and we see this band of light stretching across the sky. This image also shows two galaxies somewhat beyond ours. On the left-hand side there, you can see the large and small Magellanic Clouds. Those are seen from the southern hemisphere, and those are satellite galaxies to our own. But humans didn't know any of that at that time. We have myths and legends as how the universe worked, what those points of light were. And now we fast forward over thousands of years of human evolution and history and technology to a point where we have built enormous telescopes on tops of mountains around the world to try to understand what those points of light are and how they come together and how they explain the universe we live in. Now, this is a telescope I'm very familiar with. It's built by the European Southern Observatory. This is in Chile, in the Atacama Desert, and it has the very interesting name. It's called the Very Large Telescope. We couldn't come up with anything more creative at that point. But it's very large for two reasons. One, it has mirrors to collect faint light from very distant sources, 8 meters across, so roughly as large as this stage. It's very large for another reason, that there's actually not just one of them, but there are 4 of them all sitting on the top of the same mountain. So these telescopes have been used for roughly 20 years now, almost 25, to study the universe. We put them on top of high mountains because we want to get above as much of the Earth's atmosphere as possible. So this is another place I'm very familiar with. This is the summit of Mauna Kea, the tallest volcano in the Hawaiian chain of islands. And the telescope you see on the left-hand side there, the United Kingdom Infrared Telescope, is which I used to get my PhD back in the 1980s. And I will come all the way back to that at the end of the talk to say how we've progressed during my career. As a coincidental story, on top of this mountain, which is 4,200 meters high, I actually got married as well, because that's what geeky astronomers do. Now, even on the tops of these beautiful, amazing mountains, the weather is not always perfect. It's high, 4 kilometers high, but the clouds can be even higher, so it's not a perfect place to do astronomy. Even when you strip away the clouds, though, there's something which humans can't see so well, but our powerful telescopes can, and we can see that our own atmosphere is glowing. So this is from altitudes of 80 kilometers high, where molecules are excited in the daytime by sunlight hitting them, and in nighttime, those molecules decay. They give back that energy as light. And you see these ripples which move across the sky over periods of minutes and hours. And that can make doing astronomy very difficult when you're trying to see faint objects through a bright light. Like me, I can only see a few of you in the room here. If all the lights were turned off, I'd be able to see people in the back. So it's like fighting against a bright glow in the sky. Now, another problem with being at the bottom of the Earth's atmosphere is that it moves. And it does that through turbulence. As different temperatures move around in the atmosphere, you get a different refractive index in the atmosphere, and that makes light bend in different ways. And so this is a lovely movie of the moon. You can see it shimmering. If you were just to take all of those images and stack them all together, the image would be blurry because it's moving around all the time. So there's a kind of a limit to the sharpness that you can see if you're inside the Earth's atmosphere. We can work using lasers attached to our giant telescopes to use a technology called adaptive optics, which effectively says the laser provides me with a way of measuring how much the atmosphere is moving. If I can move a mirror in the opposite direction, I can get a stiller, more sharper image. But that only works over a limited piece of the sky. The other problem with being in the Earth's atmosphere is that it absorbs much of the light that comes from the universe. Visible light comes down to Earth. That's why we can see the sun and the stars. But at shorter wavelengths, X-rays and gamma rays, you can't see those. They get absorbed by the Earth's atmosphere. And equally so at longer wavelengths, the infrared and radio. Much of those wavelengths don't make it down to the ground. And so, of course, to measure those, we need to build satellites and put them into space, high above the Earth's atmosphere, so that absorption doesn't happen. And that you can see a gap in there between the Hubble Space Telescope in the optical and what's called the far infrared with our observatories Herschel and Planck. And that's exactly the gap where the James Webb Space Telescope fits in. Some of that can be done from the ground, but a lot of it can't. So in 1990, the Hubble Space Telescope was launched. It's been visited many times and repaired and had new instruments, cameras, and spectrographs fitted. It's still running today, nearly 34 years later. And one of the most famous things it did was this image, which is called the Hubble Deep Field, or in this case, the Hubble Ultra Deep Field. And this is the result of pointing the Hubble Space Telescope at one tiny piece of the sky and staring for almost a month, taking pictures, more and more pictures, adding them up, seeing fainter and fainter objects. So the relatively large objects here are galaxies, relatively close to us. And as you go to smaller and smaller objects in the picture, they're further and further away from us. And because they're further away, they're further back in time. So by looking for the faintest, smallest objects in this picture, galaxies so far away that they're billions of years in the past, we almost come back to the beginning of the universe, which we know was 13.8 billion years ago. So we see how stars and galaxies change over time. The galaxies at the greatest distances don't look the same as the ones which are around us today. They've evolved, just like we have over those billions of years. And we believe that somewhere close to the Big Bang, 13.8 billion years ago, there must be the first stars and galaxies that were ever born. This is not a picture, a real picture, it's a painting, showing the star formation, the birth of the first stars, around maybe 13.5 billion years ago, may be very different to the way that stars are made today in our Milky Way. The reason for that is our Milky Way was mostly, our universe was mostly only hydrogen and helium at the beginning. But over successive cycles of stars being born, stars exploding, putting material back into the universe, we now have iron, carbon, oxygen, nitrogen, the things in this room that we're made of. So that material didn't exist at the beginning of the universe. How did the first stars and planets form? Maybe they were very different. Now, that Hubble picture took a month to take. Well, you say, well, let's just keep taking pictures. Take more and more pictures with Hubble, deeper and deeper and deeper, and finally we'll see those things. Unfortunately not, and there's a reason for that. And this is called redshift. The other thing we know about the universe is expanding. It's getting bigger and bigger every day. And the further parts of the universe are expanding more rapidly. The space-time, the structure of our universe, is stretching out. And the things at the greatest distances, their light moves further and further to red wavelengths until it disappears completely from visible wavelengths. We won't be able to see it. Hubble can't see those wavelengths. So this is called redshift. That light moves into the infrared. So as we progressively move further and further back into the universe, further and further times, we use the letter Z for this, the redshift, the light all moves to longer wavelengths. And you can see now, in that very large red curve, there's almost no light left in the visible part of the spectrum. And just to give a sense, when you get to redshift of 10, that's looking back 13.2 billion years, so within 600 million years of the beginning of the universe. That's where we want to go, but there's no light left for Hubble to see. It's all moved to the infrared. And in fact, it gets worse because, of course, those distant objects, they're further away. They're also much fainter. So you not only need a telescope which now moves to the infrared, beyond visible wavelengths, but you need a much bigger one because the light coming from those distant objects is very faint. Now, there's another effect which is very important for the James Webb Space Telescope, and that has to do with temperature. Now, in this room now, the people I can see, I'm seeing by reflected light from lights maybe at a few thousand degrees. But if I was a snake in this room wandering around, and this is India, who knows, it might be possible, there might be some in the room, they see in the visible as well, but they can also sense in the infrared. They can sense your heat. That's how they hunt at night. They can actually see warm objects, mice, rodents, other things. And they're looking at lower temperatures, and they're seeing the direct heat radiation coming from those. And so as we go to lower and lower temperatures, now this is in scientific units, 300 Kelvin is roughly the temperature of this room. This is absolute temperature. So the light you're giving out directly, that a snake would see, is mostly coming out in the infrared. And if you go to longer and lower temperatures, it comes out at longer and longer wavelengths. So if we want to see heat from things at low temperatures, we need, again, to go to the infrared. Now, there's one other great advantage of going to infrared wavelengths, and that is when you look at beautiful places like this, the so-called pillars of creation in our universe. This is a picture taken by the Hubble Space Telescope. You see these giant parsec-long structures full of gas and dust, and beyond, we don't see very much because it's blocked by the dust. The light can't get through the dust. But if you go to infrared wavelengths, that same region becomes almost transparent. So if you want to see into the places where stars and planets are being born today, surrounded by gas and dust, you need to do it in the infrared to be able to get the light to come through the dust. So all of these advantages all build together. One more thing that we want to do with the James Webb Space Telescope is look at planets going around other stars. Those planets are quite cool. Maybe they're the temperature of our planet, the planet Earth. And the way we can measure their properties is by looking for stars where the planet moves in front of the star in its orbit. It goes around maybe every few days or months or years, like the planets in our solar system. And as it moves in front of the star, it blocks a tiny amount of the light coming from the star. We can't resolve, we can't have sharp enough pictures to see the planet, but the star will get a little bit dimmer for a while and then get brighter again. And then the next orbit, it gets dimmer by maybe 1% or less than 1%. And if that planet has an atmosphere, the atmosphere will absorb some light, like our atmosphere does, as I said at the beginning. And that makes the planet look a little bit bigger at some wavelengths because it absorbs those wavelengths, and at other wavelengths, it looks a little bit smaller. So by measuring the amount of light blocked from the star as a function of wavelength, we can measure the atmosphere. And it turns out that all the kind of molecules we would be interested in, water, carbon dioxide, carbon monoxide, and then things like acetylene and ammonia, those all have tracers, fingerprints, in the infrared. So all of this adds up to say we needed to build a telescope not like Hubble, which was a visible wavelength telescope, but an infrared telescope, and also a telescope that was much bigger. And there was one more thing we needed to do. We needed to build a telescope that was going to be extremely cold. And the reason for that is if you're going to look in the infrared to look at the heat all coming from the people in this room, you're all glowing. If my telescope is at room temperature, it's glowing at the same wavelength. And then I won't be able to see you. I'll be blind because the telescope is glowing. So I need the telescope to be super, super cool, which it is. It is super, super cool. So here's the Hubble Space Telescope. It has a main mirror, 2.4 meters in size. I could just about stretch that far. It's in a 12-ton satellite launched by a space shuttle, and it's in low Earth orbit at around 500 kilometers. So it's actually at roughly room temperature, it turns out. So it glows in the infrared. James Webb Space Telescope is a very different beast. It has a mirror 6.5 meters across, with 18 individual segments made out of beryllium, covered in gold, and it's completely in the open. And that's because on the other side of it, on the bottom, there's this giant sun shield, which is the size of a tennis court. And by putting the telescope on one side of that, then the sun shield, and then the sun in the other direction, the telescope doesn't get warmed up. It can get cold. And it gets to minus 230 degrees Celsius. sitting out in the coldness of space, not seeing the sun or the Earth, not being warmed by them. So it doesn't give any light out at infrared wavelengths, which makes it perfect for an infrared telescope. So here's the real machine that was built by engineers across the United States, Canada, and Europe over many years. Here it is about to go for testing into a giant vacuum chamber, which could simulate the properties of space. This was actually used for the Apollo program in the 1960s. So this is one of the biggest chambers in the world, and JWST just fit in there. Of course, we don't just need a telescope to collect light, we also need instruments to measure the light. And there are 4 different instruments on board. They look very complicated, but essentially, they're cameras, which take pictures on one hand. And then the other thing we want to do is split the light up like a rainbow to measure the spectrum, how much energy is coming at different wavelengths. And then we can use that to measure the molecules, the chemicals, the temperature, and the redshift of the objects we're looking at. So we have 4 instruments. 2 were built in Europe, partnered with the United States, 1 by Canada and 1 in the US entirely. So they look fairly small things at the back, but they're very big, very complicated instruments which took many years to build on their own. And then you attach those onto the back with the sun shield. This is the full telescope. You can see the sense of scale. There's some people here on this cherry picker. It's folded up at the moment in this configuration because, of course, it's much too big to fit inside a rocket unfolded. So we had to pack it up into the shape you see on the left-hand side here. That's the full telescope all folded up, ready to go into space. Here's the rocket coming into French Guiana in November 2021, and then everything stacked up on top, ready to go out to the launch pad in December 2021. And as I said, the launch was on Christmas Day. I was lucky enough to be there, about 5 kilometers away. If you look very carefully, you might see me in this video I'm going to show. Most of the VIPs didn't come. They stayed at home for Christmas. So it was mostly scientists and engineers, and a great privilege to be there. It's kind of emotional, this film, so I'm not going to talk. It's about 1 minute long. I'm not going to talk during it because I'll probably cry if I do. I'm going to drink some water instead.
6, 5, 4, 3, 2, unité, top.
Liftoff from a tropical rainforest to the edge of time itself, James Webb begins a voyage back to the birth of the universe. Punching a hole through the clouds, 20 seconds into the flight, good pitch program reported. Rocket continues to fly uphill in nominal fashion.
As you can see, Christmas Day, right? So, silly hats. Now, after the telescope was launched, of course, that was just the beginning of its journey, and one of the things that had to happen very quickly afterwards, as the telescope, the whole observatory left the rocket, we had to unfold a solar array on the back of the telescope to start generating power. We had batteries for maybe a few hours, so we needed that solar panel. So this actually was very emotional as well. Here's a video. It's speeded up a bit just to get it done in a quick time, but this was an amazing moment as well. So there's the telescope stacked up, not unfolded at this point, but as it moves away from the rocket over the Gulf of Aden and Somalia there, and then just a few seconds later, the satellite unfolded its solar panel, and that was a huge success. Without that, we had no mission at all, so there was lots of cheering went on. And that was the last we saw of it directly. Of course, we can see the telescope at a great distance as a point of light now, but those were the last views we had. And the next thing we had to do then was unfold it. And this was an enormously complicated process of unfolding the mirrors, unfolding that giant floppy sun shield, which had never been tested because we couldn't do that in microgravity with zero G. So it was a very nervous time, and I'm going to show you 2 weeks of absolute nervous tension in 8 seconds. The good news is it worked. So, and the enormous amount of work that, of course, went in for years beforehand to test everything to make sure that would happen was it wasn't luck, but it was extremely nerve-wracking. We went out to this location 1.5 million kilometers away from Earth, so-called L2 point, and that L2 point is a place which maintains its position with respect to Earth as the Earth goes around the sun, and that means we can hide the telescope behind the giant sun shield so that Earth and the sun are always in the same direction. And that means we don't get heated by them. That means we can get down to these extremely low temperatures. So this orbit is used by many satellites for science. It's a very interesting place, but they're not all in the same location exactly. We don't crash into each other, so don't worry about that part. Now, you came to see some data. So one of the first images that was released in 2022, and in fact this one was released by Joe Biden, is an image of, not this image I'm going to show you now. This is the old image. This is the best image taken by the Hubble Space Telescope of a giant group of galaxies. And you can see some of them have a bent in their shape. They kind of look like they're organized around the center of that picture. And that's because the gravity of a giant cluster of galaxies is bending the light of more distant galaxies, focusing that light, and that creates this kind of bent pattern. Now, the same region seen by the James Webb Space Telescope looks like this. So it's a lot better, a lot more detail. We see much further back. And just to give you a sense, as we move around, we're seeing all these very distant points of light, which are the most distant galaxies. Some of the galaxies have these very strange bent shapes, and that's, again, because of this gravitational bending of the light. So that the big galaxies are typically close to us. The tiny points of light are the ones we're really interested in, far, far away from us. And then, of course, you see all of the objects with the spikes. Those are stars, and the spikes come from the hexagonal mirror of the telescope. So that's why they have 6 points. So that picture was quite remarkable. And then we went back to the deep field that Hubble had done, the ultra-deep field. And just to give you a sense of how small this region is, with maybe 10,000 galaxies in it, it's a tiny, tiny piece of the sky, just the size of one of the craters or one of the big mare on the moon. So we're just looking at a tiny fraction of the sky, and the whole sky is full of these objects. So we went back with Hubble a few times, and you can see the image getting deeper and deeper. But then we put the James Webb Space Telescope data in that region. And this took a much shorter amount of time, just a few hours, not a month. And if you compare the images taken of just one small section, the Hubble picture is at the top, James Webb at the bottom. We see better detail, sharper images, we see fainter objects in just a few hours compared to months. And we can see in the infrared, so we can see the most distant objects, the ones that have been redshifted. So to demonstrate that, here's one patch of the sky we've been covering, looking for these very distant galaxies. And if you zoom in on one piece, that faint red dot, all the colors of that galaxy suggest that it might be a very distant object, very high redshift, maybe within only a few hundred million years of the Big Bang, all the way back in time. But to really know whether that's what it is, you need to take a spectrum. You need to split the light up into many colors and see the tracing features and see if they've moved to the red, as they should do, and that redshift will tell you how far away it is. In this case, that one worked out very well. If you look at that spectrum at the bottom, it turns out that galaxy is where we thought it was, within a few hundred million years, a couple of 100 million years of the Big Bang, one of the most distant galaxies known, one of the earliest galaxies in our universe. But it doesn't always work out. One of the galaxies elsewhere in this field was also thought to be even further away, even closer to the Big Bang. Unfortunately, that one turned out to have some tricks in its spectrum which faked being at that very large distance. So this is it's work needed to keep looking at these objects, finding candidates, going back with a telescope. So of course, a lot of people say, have you discovered the meaning of life yet with the James Webb Space Telescope? It's like, give us some time, right? We have a long journey ahead of us. We're making enormous breakthroughs, but we always have to go and follow those things up. So I have about 10 minutes left to walk you through some of the amazing number of discoveries. This is a beautiful galaxy much closer to us. This is the Hubble Space Telescope picture. You can see the center of the galaxy with the spiral arms coming out. The red regions are where young stars are being born today. The dark streaks are dust and gas where new stars will be made in the future. James Webb can take a very different view of that and look at the glowing gas and dust at lower temperatures. And so that exact same galaxy with JWST looks very different indeed. And we can see structures, bubbles in there, which have been blown out by previous generations of star formation. And we're taking many of these images. So there's a whole gallery, all available online, which people are using to study how galaxies change over time. We can then come much closer to home. We can look in our own solar system, and we see our planets literally in a different light. When we look in the infrared, we can see the molecules in the atmospheres of those planets absorbing light. So Saturn is amazingly dark here compared to its rings. Its rings are made of ice and reflect almost all wavelengths very well, but its atmosphere has lots of methane in it, and that methane in the infrared absorbs the sunlight falling on it, so it makes the planet dark. And of course, there are moons there in the same image. We can go further out in our solar system. This is the planet Uranus, which lies on its side and has rings around it as well. And many of the blue points of light in that picture are its moons. And those moons, many of them are icy, so very reflective, again, in the infrared. And then you have the planet Jupiter, which seems very different in the infrared because we're looking again at different molecules. We can also see the red glow of an aurora at the north and south pole of Jupiter. So those planets are in our own solar system. What about planets at huge distances? This again, it is an artist impression. JWST can see some planets going around other stars, but in most cases, we measure them again as the planet moves in front of the star gets a little bit darker for a few hours and gets brighter again. And as I explained at the beginning, if you measure that dimming at different wavelengths, you can tell something about the atmosphere of the planet. If the atmosphere is absorbing light, it makes the planet look a bit bigger. At another wavelength, it might be transmitting that light. It looks a bit smaller. And so we can reconstruct the atmosphere of a planet by making these measurements, and we can see what you can't read the symbols there, but there's water, there's carbon dioxide, carbon monoxide, there's sulfur dioxide. There are all sorts of things, molecules at relatively low temperatures in these planets' atmospheres. So people say, will James Webb Space Telescope see evidence for life on other planets? Probably not. It's not designed to do that. But what it will do is find planets where the atmospheres have the properties like Earth or like Mars or like the planets in our own solar system. And that will allow us to target those planets with telescopes in the future, even more detail, and look then for things like ozone and other molecules which are linked, on our planet at least, to non-equilibrium chemistry, which indicates life. So this is a huge, complex field which many people are working on. But I want then to talk about the bit in between those most distant galaxies and the planets and how they're born in our Milky Way today. So let's go back again to the pillars of creation, as they were called in this Hubble Space Telescope picture. This was taken in 1995, hugely influential, front covers of all sorts of magazines. And many people said, in fact, that it was this image which led politicians to give the money for the James Webb Space Telescope, because it was such a big hit in '95. So we owe a lot to this. But again, James Webb, with its infrared capability, has a very different view on that same region. So now those pillars are much more transparent. we can see inside them. And if we look at the full scale here, as we move up the pillars, the orange and yellow gas are molecules glowing under the ultraviolet light, the illumination like me with the lights here from big stars nearby. And the red patches are places where young stars are being born today inside those pillars. And we can move to longer wavelengths, taken again by the James Webb Space Telescope with a bit different instrument, and we can see a whole nother view. And this is the one I call the Harry Potter view of M16, as you will understand. There are the Death Eaters flying through the universe. So we can look at star formation in many, many ways, and we want to understand how material is gathered together to form a star, how some of that material turns into planets. But there's a process which is really important in all of this. As the material collapses together, it's spinning slightly, and as it gets more and more compact, it spins faster and faster and faster. Like me, I'm not going to do this because I'll fall over. If I was an ice skater and I span around and then pull my arms in, I would spin faster and faster. This is called conservation of angular momentum. And the same thing applies as material is gathered into stars. And you have to get rid of some of that angular momentum in order for the star to be able to collapse. Otherwise, it will spin so fast it will fly apart. And the phenomenon which does that is called a jet, or an outflow. So here's a young star-forming region. And right there is an object we discovered in the 1990s. It's a jet of material. This linear feature here is material being ejected from a young star. At the same time as the baby star is trying to swallow material, it also ejects material. And if you think about human babies, that's pretty much the same story, right? You put some food in, and it comes out both ends. Not all of it, else they wouldn't get bigger. So it's only a small fraction. And with the James Webb Space Telescope, we're able to zoom in with much more detail now, much sharper pictures. And this is what we saw last year. And we see much more detail now in that jet. I'm going to put a green dot on the picture to show you where the young star is. So we can't see it in these pictures. That young star is completely covered in gas and dust, but we can see the material moving away, and we see that jet wiggling its way out. We can also break that light up and measure this spectrum, very complex set of lines at different wavelengths that tells us the properties of this jet. What's it made of? What kind of gases are in there? What molecules? And in fact, the discovery in here in our paper was that it was almost entirely made of molecules, like carbon monoxide in particular. So we had this on the front cover of Nature just last year, these very young jets. This may only be 5,000 or 10,000 years old, so it's the very first stages of a star being born. Another example, near the Horsehead Nebula in Orion, which also we discovered in the late 80s, early 90s, is an object which has a number, HH212. And this is a picture we took with the telescope I showed you right at the beginning, the very large telescope, from the ground in around the year 2000. And this is showing that material. You can more or less work out immediately where the center of that must be because it's so symmetric. Right in the dark part in the middle is where the light's coming out. And now if I show you the JWST picture taken last year, so around 20 years later, firstly, it's much sharper. We see much more detail. But if you were watching carefully, it moved. So I'm going to go back to the other image. Did you see? It shrank. And if I push it out again, it moves. So the gases are moving out at about 100 kilometers per second, pretty fast. But over 20 years, we can see that at that huge distance with our telescope. So this is remarkable. Now, the place where I've spent most of my career, I mean, at least in my head, I haven't really been there, but the place I've spent most of the time studying is one of the most famous star-forming regions in our Milky Way galaxy. So these are some of the beautiful pictures of other star-forming regions made by the JWST. But let me show you the most important place, at least for me, and that's in the constellation of Orion. So you're probably familiar with Orion, with Betelgeuse and Rigel and the other stars making up the shoulders and the feet, the belt. And then hanging below the belt is this slightly fuzzy patch, which we call the sword of Orion. And the sword of Orion, if you zoom in detail to the Hubble Space Telescope, looks like this. This is a region with very, very hot stars in the middle, which are glowing at ultraviolet wavelengths. They're then breaking gas apart and exciting the gas and making it glow, so making this nebula. Much of this is hydrogen emission. You can see a few other stars in there around the center. You don't see too many, though, and that's because we're at visible wavelengths. If you want to see all the young stars being born, firstly, they're a bit cooler. Secondly, they're covered in gas and dust. We need to go to the infrared to see the other stars. And so my PhD thesis on the telescope I showed right at the beginning, the United Kingdom Infrared Telescope, we started by taking this picture in 1986. So this was with crude technology. It was the best you could do at the time. It was amazing. But suddenly we see hundreds of young stars in the same region. These are around 1 million years old. And then a year later, we managed to take a color image by combining light from different wavelengths. And then around 10 years later, we used the VLT. The picture became even better, even sharper. But James Webb Space Telescope has changed our view completely. So now we have enormously sharper images covering the same region. Let me just zoom in a little bit. I can't, in the time left, I have a minute or two left, I can't share you the incredible detail in this picture. This picture is 21,000 pixels wide. Even that enormous sphere in Las Vegas doesn't have enough pixels to show this image properly. So if you go online, you can find this image and zoom around, and you might find things like this. These are young planetary systems, young solar systems, being made today going around stars. So you can kind of see that there's light, bright light at the middle in some cases, and then there's dark dust and gas swirling around, making planets. And that's blocking the light from behind it, from the nebula. So we see these things as silhouettes, as shadows against the background. Those are young planet systems being born today in the Orion Nebula. And if we zoom back out again to the large scale, then we go back into just this small region here, then we see something very curious, a complete discovery by James Webb, something we discovered last year and which blew our minds completely. If I draw your attention to these objects, in each case, there are pairs of faint objects close to each other, and that's not by chance. They belong to each other. They're so-called binaries. Each one of those objects is the mass of a few times Jupiter. So these are planets floating freely without a star, just floating freely as pairs. And we call them Jupiter mass binary objects, or jumbos. And we're better to talk about jumbos or elephants than in India. So we gave this name to them, jumbos, and we're still trying to puzzle out how they're there. They shouldn't be there. They should not have formed in a region like Orion. There's lots of theory that people say, no, they don't exist. They don't exist. They do. So we need to understand how they work. And if we go back out to the wide field picture again, not only can we see it at these wavelengths, well, it's James Webb. We have lots of other wavelengths to play with. So there's a huge amount to discover in this image and in the many images and the spectra we're taking with the James Webb Space Telescope. We think it has a lifetime now of around 20 years, much longer than anticipated because that launch in 2021 was so perfect, it saved so much fuel that this is something for generations to come. And everybody can use it. Even though it was built by North America and Europe, it's free for everybody in the world. It won't be easy to compete to get time on it. It's oversubscribed enormously, but anybody in this room, in principle, can write a telescope proposal to use this. And so there's a personal journey here as well. Once upon a time, I had hair. That was me getting my PhD thesis or just before my exam in 1987. And it was just such a privilege to spend a great fraction of my career, 26 years up to date, working on a project with 20,000 others, sponsored, if you like, by 1 billion taxpayers on behalf of 8 billion people to try and discover our origins. Where did we come from? What's the fate of the universe? How did consciousness arise? I think this is a perfect conference to talk about what human beings can achieve when they set their mind to it in collaboration together, because there are so many technological challenges which face us on this planet today. Maybe by looking at these inspiring pictures of what we know about the universe, maybe we can put our power to solving climate change, resources which are depleting, the many other challenges we have on this planet. I'm optimistic about that. I won't say I'm wholly optimistic about some of the methods that some of people at this conference have talked about to solving those problems, but that's maybe for another time. I think human ingenuity together, creativity, curiosity, we can do astonishing things. So it's been my privilege to talk to you today. Dhanyavad. Thank you. And I will steal, can I steal 30 more seconds from you? Because if you're inspired by what we do, if you can put the slide back up, we run an outreach series called Space Rocks in Europe, and we'll be very willing to come to India. We bring astronauts, musicians, actors, filmmakers together. There's a whole series of YouTube videos where we've talked to people, diverse people, astronauts, musicians, many people from Star Wars and The Expanse and Battlestar Galactica. Please go online and look for Space Rocks uplink. They're all free there to view, and I look forward to talking to some of you outside at lunchtime. Thank you very much. Thank you.